Hello students, welcome to our channel Simplified Computer Science Concepts by Professor Rutuja. Today we will be learning centralized deadlock detection algorithm in distributed systems. So let us begin. So this centralized deadlock detection algorithm, the name itself suggests what does centralized means. That means some activity is going to be performed in some central manner, or some central node is going to coordinate the activities between the sites. Now there are sites. So there is a site 1 which has certain resources and processes into it. So here resource 1 is assigned to process P1. P1 is requesting resource R2 and this resource R2 is already assigned to P2. This is the local wait for graph of site 1. There is another site S2. This site also maintains its local graph, wait for graph, and here process P3 is assigned with resource R3 and it is waiting for resource R1 which is at site 1. Then here, as I've told you, centralized means there is a central node. So here it is a coordinator. This coordinator is a central node or a central site or a designated site which will maintain the union of these two sites. So if you just see, this part is over here and the site 2 local wait for graph is maintained over here. So the wait for graph at coordinator is nothing but the union of the two local graphs of the each site. Now here the coordinator sees, is there a cycle into this local wait for graph of the coordinator? No, cycle is not there. So if no cycle, that means no deadlock. But if cycle was found by the coordinator into this local into its wait for graph, then a deadlock would be detected. So here the coordinator is the one who will take the decision on which particular process should be killed and from which machine it should be killed, so that the deadlock would be resolved. So let us consider this situation. The situation after delayed message. So let's say this is the wait for graph at the coordinator, wherein now the process P2 has released R2 because it has utilized it. So this was the release message and now it is requesting for the resource R3 which was at site 2. So two events are occurring, that is P2 releases R2. So process P2 is releasing the R2 resource, and at the same time P2 is asking for a resource R3 which is at site 2. Now two messages will be sent. Which are the two messages? First is of releasing the message, releasing the R2 message, and the second one is waiting for R3 resource. Now this should cause no problem. So if you just observe this wait for graph at the coordinator, is there a cycle formed? No, there is no cycle formed, which means straight away there is no deadlock. But then if you just assume that the message 2, this is the message 2, that is the requesting message of resource R3, it arrives first and the releasing message of R2 has not yet been arrived at the coordinator. So the coordinator will see the wait for graph in this fashion, which means that there is a cycle into this, and when there is a cycle there is a deadlock. But actually if you see, there should be no deadlock because P2 has already released it. But due to the message that has not been arrived at coordinator, and the second message, that is the requesting R3 message, has arrived first, it leads to deadlock. And that particular type of a deadlock is called as a false deadlock, or it is also called as a phantom deadlock. So the solution here is to use the Lamport's algorithm, which will impose global time ordering on all the machines. So here what will the coordinator do? Coordinator will judge that he has received some improper activity. So it will send the message to the machine saying that I have received a message of so and so timestamp. Do you have messages smaller than that? If So the machines will be replying either positively or negatively, and accordingly the coordinator will kill that particular process from the machine and the deadlock would be resolved. So see, alternatively, if the coordinator suspects deadlock, it can send a reliable message to every machine asking whether it has any release messages. Each machine will then respond with either a release message or a message indicating that there is nothing to release. So this is how the centralized deadlock detection algorithm in distributed system works. And there is this demerits of centralized detection algorithm, that is due to if this central activity that is there, that means the coordinator or the designated site, if that designated site fails, then the entire system fails. So that is called as a single point of failure. And obviously there will be a lot of bottleneck, that is network traffic or congestion around the sites due to lot of wait for graph information messages are passing. So this is one of the main demerits of centralized distributed deadlock detection algorithms. That's it. So thank you. Please do like, share and subscribe to the channel. If you have any comments, please do post in the comment box. Thank you for watching the video.